Let us have a big picture of sampling and reconstruction from samples. Assume that this is signal in time domain. If you apply Fourier transform, we assume that in frequency domain, it is band limited. That means that outside of these bandwidths below frequencies smaller than -w and above w, there is no frequency component. The sampling is to multiply this signal x of t by a pulse train, by this signal. So you multiply the signal x of t by this pulse train. That means that in between the samples, this pulse train here is 0, so you multiply these and you don't take these values. But when you have a delta Kronecker, you take this sample and you multiply these, you take this one. And because the height of all these samples is equal to 1, so when you have the product, you have only the values of the samples. What happens is that the Fourier transform of this pulse train is also a pulse train, because you do multiplication here, you multiply these two signals. In frequency domain, you need to convolve them, so you do convolution. So you convolve these band limited signal with this pulse train again. So what happens is that when you multiply these two signals, when you multiply these and these, then the result is going to be the signal, which is here, the sum at the sample value. So you take the sample at this point, then you take the sample at this, and so on. Now, if you convolve this signal in Fourier domain with this pulse train, means that you get convolution of this one, it goes inside the summation, and then you get convolution of these with each individual delta function. Obviously, when you convolve this guy with this one, means that you get this one and then shift it in frequency domain. So you will have this guy, if k equals 0, you will get this pulse shape. For k equal 1, you convolve x of f with x of f, delta of x of f minus fs. That means that you shift it. So whatever is at frequency 0 will be at frequency fs. So, and then you add them together. So you will have this Fourier transform of the signal plus all its replicas equally distanced with fs. So what happens is that if your bandwidth here is w, here is fs, therefore here is fs plus w, and this frequency, which was minus w, is shifted with fs, so you get fs minus w. So the idea is that if you want to recover your signal in frequency domain, this w should be smaller than fs minus w. Otherwise, the upper side of your Fourier transform will have an aliasing with the lower side of frequency domain component of x of f. So if you have this condition, which is the Nyquist rate sampling, then you can recover your x of f just by applying a reconstruction filter. The reconstruction filter needs to be equal to 1 within the bandwidth of signal, and it should be 0 outside. But in between fs minus w and w, which is guard bound, you could have any arbitrary value, which allows you to design your filter more efficiently.